Imagine a massive container ship or oil tanker weighing hundreds of thousands of tons floating calmly in a bay. It looks completely still, but there are no brakes on a ship, no wheels, no friction with the ground. So how does something so enormous stay exactly in one place when wind, waves, and currents are constantly pushing against it? The answer lies in one of the oldest and most clever pieces of maritime engineering, the ship's anchor system. Most people picture an anchor as a big metal hook that simply grabs the seabed and holds the ship like a dog on a leash. That's the grappling hook myth. In reality, modern ship anchors rely on complex physics, the weight of hundreds of meters of heavy chain, and careful operational procedures. The anchor itself is only part of the story, often the smaller part. Let's break down how it really works, step by step. When a captain decides to anchor, the ship approaches a suitable spot with good holding ground, preferably soft mud or sand, not rock or thick seaweed. The crew prepares the anchor on the forecastle. Then the order is given. Let go the anchor. The anchor drops, falls through the water, and hits the seabed. But the captain doesn't stop there. The ship continues to move slowly astern while the crew pays out a lot of chain, much more than the water depth. Why so much chain? This is where the magic happens. The catenary curve. The heavy anchor chain sinks and forms a long, sagging curve along the seabed. Mathematicians call this shape a catenary, the same natural curve you see in suspension bridge cables or a hanging chain between 2 points. This curve does two incredibly important things. First, it acts like a giant underwater shock absorber. When wind or waves push the ship backward, the ship doesn't yank directly on the anchor. Instead, it has to lift this heavy belly of chain off the seabed first. All that energy is spent fighting the weight and friction of the chain. The pull on the anchor itself remains low and mostly horizontal, exactly what you want. Second, the horizontal pull forces the anchor's flukes, the pointed shovel-like parts, to dig deeper into the mud or sand. The harder the ship tugs, the deeper the anchor buries itself, creating both mechanical grip and powerful suction from the surrounding sediment. So in moderate conditions, the ship is held more by the weight and friction of the chain lying on the bottom than by the anchor hooking anything. The anchor's job is mainly to provide the initial grip and prevent the chain from dragging. The chain provides the holding power and the shock absorption. Now, how do captains know exactly how much chain to let out? They don't guess. Anchor chain is marked in standard lengths called shots or shackles. One shot is usually 15 fathoms, about 27.4 meters, 90 feet. On most ships, every shot is marked with color-coded paint on the links or detachable Kenter shackles. Common systems use red, yellow, blue, white, and green in a memorable order. One popular mnemonic is "Rub your balls with grease." Red, yellow, blue, white, green. The markings tell the officer on the forecastle exactly how many shots are out. For example, in 20 meters of water, you might put out 5 to 7 shots, depending on weather, to achieve a good scope ratio, usually 5 to 1 to 7 to 1 or more in strong conditions. More chain means a flatter angle and better holding. In very deep water, say deeper than 100 to 150 meters, ships usually cannot anchor at all. Even the largest vessels carry only enough chain for relatively shallow coastal waters. In the middle of the ocean, the water can be thousands of meters deep. The chain would never reach the bottom, or if it did, there wouldn't be enough left to form the crucial catenary curve. That's why ships drift, use dynamic positioning systems with thrusters, or simply keep moving in open ocean. When it's time to leave, retrieving the anchor is no simple task. The captain slowly moves the ship forward over the anchor while the windlass hauls in the chain. As tension increases, the anchor must break out, overcome the powerful suction and grip it has created in the mud. This can be surprisingly difficult. Crews sometimes have to use the ship's engines to help break the suction. Once free, the anchor is brought up, often covered in thick mud. Deck crew then use high-pressure hoses to clean it before it's secured back in the hawse pipe. The entire process, from letting go to weighing anchor, requires precise coordination, good communication between bridge and forecastle, and respect for the enormous forces involved. A dragging anchor or fouled chain can quickly turn dangerous. So the next time you see a ship calmly anchored in a harbor, remember, it's not just hanging from a big hook. It's being held by thousands of tons of heavy chain forming a clever mathematical curve, combined with an anchor that digs itself deeper the harder it's pulled. It's a beautiful example of practical engineering that has kept ships safe for centuries, using physics instead of brute force. What do you think? Did you know the chain does most of the work? Or that ships can't anchor in the deep ocean? Which part surprised you the most? Drop your thoughts in the comments. I read every single one.